would like to start my talk with congratulating the 3 laureates and also thanking them for being a friend, a colleague, a mentor, and a hero for me. And I think throughout the talk you'll be able to see what kind of impact they had on my work, because certainly with Jörn and with Connie there is some overlap, and I think you should take that as this is really important if it comes up 2 or 3 times in a day. So today I will talk about the internal structures of low-mass stars, and just as a reminder, I put up here a Hertzsprung-Russell diagram where we have the color or the temperature on the x-axis and the brightness on the y-axis. The main sequence is very nicely shown here, and because I talk about low-mass stars, the mass evolution is important. So we have the low-mass stars on the right bottom, and moving up to the higher masses that Connie is interested and showed in blue. They're also in blue here at the top left. So the stars that I will mainly discuss are in this area, indicated with the red circle. And so these overlap with the stars that Jörn is interested in. Low mass main sequence stars, subgiants, and red giant stars. You may well comment that there is a lot of big branch here, and I used a stick. Here with also low mass stars, because I told you the mass goes up in that direction. And we would all be very much interested if we could also probe that part of the HR diagram. But unfortunately, the periods of the oscillations and their amplitudes are pretty difficult, and certainly the combination to observe them. There are efforts going on, but it is not that we can probe that. So we stick around here a little bit at around 1 solar mass, maybe up to 2 solar mass. That is what I call a low mass star. Okay, so that was an observational diagram that I just showed you, and I now move on to some theory. And so if we take this 1 solar mass star, this will move through in evolution through this diagram. So again, we have the temperature here on the x-axis and the luminosity on the y-axis. And what you can see is that from A to B to C, the star evolves. And so between A and B, it is a main sequence star, and it's just burning hydrogen in its core. I must note that these small figures in the bottom are not to scale. And then if we move from B to G, so that's quite a big part here in the diagram on the top, we have this subgiant and red giant branch star where we have a hydrogen burning shell around an inert helium core. Jörn called the core quite boring, and indeed there's nothing much happening there. Then we move on here at H, so I'm, as Connie, a bit too short, but there at H we have the stars where we have had the onset of helium burning in the core, and then after that, if it evolves further up, we have a asymptotic giant branch star where we have also helium burning shell around a CO inert core. So these pictures here in the bottom are very, very schematic. We can put this a little bit more scientific if we look here at what's called a Kippenhahn diagram. And so what we see here, we again look in the evolution of the star. We have the core here at the bottom, and we have always the surface at the top. And then every kind of vertical line here is the structure of a star at a particular age. And so the age goes from left to right, and we can see that here from 0 to, say, roughly 8 gigayears, we have a very similar structure. We have a hydrogen fusion in the core, a radiative region, and a convection region. And we've already heard this morning that this convection is very important in the convection, and you see that at least in mass it's only a very tiny layer. In radius it would be a bit more. And then at about 8 gigayears, there is no hydrogen left in the core. We go to a thick shell burning, and the rest of the structure doesn't change that much. And then here at 11 point something gigayear, we will move to a thin shell burning, and actually we come into the really red giant branch, which gets a much bigger convective core. And then evolution also increases. Here we are at the nuclear time scale. We get to a thermal time scale here. And you can see that in a relatively short amount of time, we have big changes here where the convection zone is receding, and then we have also the onset of the helium burning in the core, and you can see the convective core that Jörn also already pointed out. And here at the top you can see the labels also. You can follow that here in the Hertzsprung-Russell diagram. Sorry, this microphone is not functioning. Yeah. Okay, so also we need some data. So this was a very theoretical picture. We need data, and I've very schematically showing here what the evolution of the data is that we had. So we started out around the 2000s with, before that was discussion, you're ensured that in 1995, Hans Kelsen already published the first star. But around the 2000s, we got from ground-based observations the first few stars that were observed, but it was individual numbers. Then we got the Corot mission, that's a French-led mission, and that increased. We got of the order of 1,000 or so solar-like oscillators or oscillations in low-mass stars. Then we had Kepler coming up, and later also transformed in the K2 mission, and we got many, many, many more stars. We're now, as Connie already said, we're in the TESS era, and again, TESS is taking lots and lots and lots of stars. And we will move into the future with Plato, that has been mentioned already and is on the books to be launched at the end of 2026. And there are some efforts for the future with the Earth 2.0 and the Nancy Grace Roman. The latter is not really made for astroseismology, but there are efforts to also include that in the science case. And so what I wanted to show here is that we now have many, many, many stars in this low mass regime where we can actually get the oscillations. You have to keep in mind that the quality is not always the same. So some of these missions have much longer time series than others, which makes a difference because the longer time series gives us a much better resolution power. Others have bigger and smaller pictures, so also the photometric accuracy is different. So in terms of the numbers, these are also all photometric missions. All the space missions are photometric. If we do ground-based observations, and it's still going on with, for instance, the Song Initiative, the numbers are not as large, but we get different information, so that's also important. So this doesn't tell you all, but at least tells you that we have lots of data to analyze. And so what does this data look like? Well, this is a typical time series that we look for a red giant star, which is one of my pet stars. And I only show you here 20 days, but we have for this star 4 years. But if I would show you that, there was nothing to see. And you can see, so this is the raw data essentially that we get in. That's a bit difficult to analyze, and that's why we take a Fourier transform, and then it looks like this. And this is very beautiful in my opinion. And we see all these peaks, and we have the challenge of identifying them, which in this case is not very difficult, let's say it that way. And so we can readily identify here the radial modes. So I have a small movie. Again, you've seen this before. Radial modes are identifiable in this diagram. On top of that, we also have the quadruple or LS2 modes. They are identified quite next to it. This was also already alluded. This is similar pattern as for the Sun. And then we have many modes in between. And those are the ones that are most of them are dipole modes. There may be an LS3 mode here and there, but not that many. And as Jorn already indicated, those are these mixed modes that carry also information from the core, which is quite interesting and provides us with lots of measurements. Okay, so we have this data. What can we do with it? So what we typically do, we take the data and we confront them with models. And so we have some stellar evolution codes. So one of the most used codes at the moment is the MESA, but I put here Aztec because that's developed by Jørn Christensen Dalsgaard. And these give us stellar evolution. And then we also compute the oscillations, again, gyre and adipose developed by Jørn. And so then we have the models, so we have the data, and we need to match them. And we can again do that in 2 different ways. So we can do a forward problem. So we say, okay, this is our data. We make a model, check. Does it work? No. Go back, make a slightly different model, and check. That's a forward model. And that's great. And we can, with the current knowledge of our models, we can maybe match the data. What we can also do is kind of the inverse problem. And we can say, look, we have this data. And maybe we can now find out what the model should look like given this data. Because of the oscillations being sensitive in different parts of the star, we can do this. So I first want to show you a result of the forward modeling problem. And that is done by my student, Lynn. And these are just 2 random main sequence stars. And you see again the different degrees are indicated. So we have here the 0 and 2 pairs in blue and orange. And then we have in black and red, we have the 1 and 3. So in these main sequence stars, we have LS3 modes visible. And in the filled symbols, we have the data. And then in the open symbols are what we call a best fit model. Well, I think it's quite reasonable, I would say. However, there's still, certainly at the top where I can't point, there are differences between the models and the data. And so it's quite hard if you just look at this and you say, yeah, okay, that's different. Okay, we can agree on that. But how do we now solve this issue? Where in the star should we, or in a model, should we change what to solve this? And that, I think, is the interest of the inverse problem, because we can much more directly probe in the star and say, hey, here something is going wrong and it goes in this direction, so maybe we can really look what is the physics that we need to change. And that is what I think is the most interesting part of this. And so we can do inversions, and I just wanted to show you here some first results by Jörn. So this is the first time that inversions were done. So these are structure inversions, and this is indeed from 1985. You will see some improved figures, I would say. But you can see here already, so this is again the sound speed, the relative sound speed difference between what is a best fit model and the data. So it's relatively model independent, but there's still a model as a reference here. And you can see already in 1985, it is less than 5% difference. So it is 5% difference, which could definitely be improved and has been improved in the meantime, but it was only 5% difference, which also showed that the models were not that bad at the time. But still improvements could be made. And then it has taken quite a while till also this kind of technique could be used on other stars. The reason for that is it's twofold, essentially. So for the sun, we know the mass and the radius very, very accurately. And that is one of the things that is useful if you want to make a best fit model. And we don't know it as accurately for any other star, of course. The second reason is that for the sun, and Douglas alluded on that we have thousands of oscillation modes. But obviously for stars, they cancel out, and Jörn showed very nicely, we maybe up to LS3 modes, but the rest is not visible. So we have much less information from the oscillations. Nevertheless, the Kepler mission has provided a great source here, and so it has been possible to do also inversions on other stars than the sun. And here's an example from 2017 from my former PhD student, where we did 16Sig. You can also see that, first of all, it's a slightly different parameter, but it's still related to the sound speed. But you can see that we go there to very different numbers on the y-axis. So here we are not above 4%, and there it's 20%. So also the uncertainties, the inaccuracies are larger. And the other thing that you can see is that the x-axis here goes from 0 to 1, where there's actually no information between 0.15 or so. If you now look at the top picture, it only goes up to 0.4, and we have actually most of the information deeper. So this is also one of the things that are very interesting, that even for the, we can probe a very different parameter space, essentially. So we cannot say anything about the outer layers of these stars, but we can probe the inner layers. So then a recent result published this year from Lin, where we have done not only 16Sig, but we now have results for 12 stars with radiative cores. And this is one of these results. So again, we have the fractional radius up to 0.3 roughly. And we look here at the dimensionless isothermal sound speed. And you can see that for this particular star, the telephone number is in the top, you can see that we have quite a significant change between the model and the data. And this is really one of the key things that we are looking for. And the interesting thing is, if we look at all 12 stars, is that the picture is not uniform. So we do not see that for all these stars, they're overestimated or underestimated. We see a variety. So there in the top panels, we see that it is a positive deviation, but here it is also sometimes negative, or we have really nice results between the model and the data. And so we're looking forward what we now can change. And one of the things that we have seen is that the deviations seem to scale with the evolution and the mass of the star. So the more evolved and the more massive stars have larger deviations, which does point us to potentially the CNO reaction rates. We have done some tests, and that's not conclusive at the moment, but at least now we have a clue where to look for things. And we didn't have that at all with the forward modeling. So this is on main sequence stars. We also have been able to do a subgiant. Earl did this, and here this is the first result of a subgiant, and it's shown it slightly differently. So we have the sound speed here. We have 4 different models, and we checked if there's a real big difference. But you see that all 4 models give us relatively similar results, but still there are significant discrepancy if we would have compared that. So again, we have to look here for something that can be changed. Answers are still in the open. Okay, so we have now moved from we move now from the main sequence to the subgiants, and I would like to move to the red giants. And you see now not only 1 stellar evolution track, but 2, so one for 1 solar mass star and one for 3 solar mass star. And you can see that here they are very far apart, and so we would potentially be able to, based on the luminosity and the temperature, distinguish between things. But you get here, you get much closer together. And you can imagine if we add more masses, maybe change our metallicities, that things change there as well. And so it will become very hard from observations from just luminosity and temperatures to distinguish between stars of different masses and also of different evolutionary stages. So we have here on this side, we have the RGB stars, and there we have the core helium burning stars. And so we cannot always distinguish between those types in our observations. And as Jörn showed, it's exactly the same figure, that we have these 2 power density spectra, and the LS0 modes are lined up very nicely, and so from that perspective, these stars are the same. The LS0 modes essentially show us the mean density of the star, and so these stars are indeed quite equal. But as Jörn also said, is that the star is very big, and it's only a tiny core, so we wouldn't see that. But now if we look at the LS1 modes, I zoom in for you, which Jörn didn't do, at least something different. You can really see that for the 2 ones, it is quite different if you look at this. And here, if you look at the periods, so at the difference between these peaks, and we look now in period, because this is indeed the gravity modes that we're looking at, that is definitely not the same. And so because we now got the information from the core, and the stars are only different in the core, this is what we can use. And so this is the full diagram where this was the first diagram, Jörn showed a later one, where we measured these period spacings for the different types of stars, and we can clearly see that we distinguish between stars with a helium burning core and stars without a helium burning core, so under RGB. And so this has been a very big result in the field, also because this is important for something like galactic archaeology, which Andrea Miglio will speak about later this afternoon. Okay, one of the things, if we then now look at the core helium burning stars, is very interesting, because if we look at those stars and we observe the period spacings, and that's done in all these orange dots here, so these are different stars for which we have measured it, and we look at the models are indicated here in the black dots, and the gray area is a little bit the area we can cover if we change some of the physics. You can clearly see that the models do not go up as high values as the data go. There's a clear gap there. And this is, again, an indication that something is missing in our models. And so we have been looking at this because the 2 obvious candidates for this mismatch, essentially, is the convective boundary mixing. So that is where we have the convective core and then the transition to the radiative region. How do we treat that in our models? That is a big open question. And the other is the nuclear reaction rates. And so one of the very uncertain, but the most uncertain reaction rate is the carbon alpha reaction rate. And the reason we cannot measure that is that we always have to extrapolate. So there's a measurement in the lab, but obviously the conditions in the lab are very different than we have in the stars. So what we have done here, we have looked at first the observations. So we have here kind of the observations summarized in period, And as I can go back, you can see they're not very mass dependent. So we've taken the mass as not important here. And we just have the opacity here is the number of stars. So most of the stars are kind of there. And then we do here on the left-hand side, we have the models. We take different metallicities, so minus 0.50 and plus 0.2, because also the metallicity, of course, has an impact. We change the reaction rates by what is normally used, half of it and double it. And then we took, in this case, the semi-convection, which is just one of the prescriptions we can use for the convective boundary mixing. And what you can clearly see here is that in this prescription, we do not reach these high period spacing values. Just not. It's not possible with our models. So now we checked, and we take some other prescriptions of the core boundary mixing, and so it's maximal overshoot, overmixing, and penetrative convection. For the moment, it is not so important what they exactly describe, but you can see that the picture changes. And there are now cases where we can really match these large period spacings. It is still not conclusive which core boundary mixing scheme and which reaction rates we should use, but at least we are now sure that we can find the physics that is important. And so this is ongoing work by Anthony Knoll to figure out what would be the best combination of convective boundary mixing and nuclear reaction rates to really explain these stars. And so again, a mismatch between our models and the data, astroseismic data, are really helping us to infer the internal structures of these low mass stars. Okay, then we go to the last topic, and as everybody talks about rotation, I felt I should not be left out here because rotation is indeed very important. So I have this small movie made by Andrea Miglio where we have the stars here on the top. This is all LS1, so one nodal line on the surface. We have where we just have no impact from the rotation here in the middle, and I go back, it's not, yeah. And you can see here on the amplitudes and the periods of the peaks. So you can see if the rotation goes with or against, the pulsation goes with or against the rotation, that you have a slight change in your period or in the frequency. So you get the splitting of the mode. And then you can also see that if the way we look at it, what is the, the inclination axis, which modes are really clearly visible. And so this has been done, and I show you just one result here. This is by Paul Beck, where we have, again, the power density spectrum indicated with the 0 and 2 modes, and then here we can focus on this side on the LS1 modes. You can see that there's these few peaks here together and these few peaks there. That's different mixed modes. And then you can again see that they're split, and that is what is the rotational splitting. And if you measure that, you can see this pronounced V shape that we have there. And in this work, there was no detailed modeling going on, but at least we modeled roughly the stars. And if we put it in a solid body rotation, which is a very easy assumption, that's a good starting point, we don't get the V shape, we get a head shaped very clearly. And so that's not consistent. But if the fast core, so the core is rotating 10 times as fast as the surface, you get the V-shaped reproduced with roughly the same order of magnitude. And as Connie already pointed out, this is actually a problem because the core is only 10 times faster than the surface. And we would have expected that very different. So the models and the data are very different in this case. And this is still also, again, an area where a lot of work is ongoing, how to include more prescriptions of angular momentum to make the models and the data aligned. Okay, just to finish off what I've discussed on internal structures of low mass stars. So first I showed about the inversion results where we have clear indications that some of the physics in the model needs to be included, at least in a number of stars, but not in all stars. We discussed that the oscillations are now sensitive to the core, and we can really distinguish between different evolutionary phases. We've looked at the convective boundary mixing and the nuclear reaction rates in the core helium burning stars, and the rotation is 10 times faster. So These are just some examples of what we are doing for low mass stars using astroseismology to infer the internal structures. There's of course much more going on in the field, but these I thought were interesting things to show here. Thank you very much for your attention.